come back from the break, we take your questions, and then we close session. So for today's topic, the objectives include: we are going to learn to understand the concept of the gravitational field. Then we shall state the relationship between the gravitational constant g and acceleration due to gravity. We will learn to calculate the escape velocity of the Earth, and then we shall state some effects and applications of the gravitational field. But before we start, let's define force. A force is a parameter that changes the state of an object. Let's say we have an object at rest. This object is at rest. This object will continue to be at rest until a force acts on this object. So we say that a force is a quantity that causes motion, because without a force, there won't be motion. And at the other end, so if this ball is in motion, if the ball is in motion, we need to apply a force to stop the movement of the what? Of the ball. So a force is a parameter or quantity that changes the state of an object. We have two types of forces. We have contact forces, and then we have force fields. Contact forces require a direct contact with the object. For example, now, I'm holding this marker now. I can apply a force to this marker now because the marker is in direct contact with my hand. Another example is I'm holding this duster now. I can push this duster like this and push it back like this. That's contact forces. Examples of contact forces are: we have pull, we have push, we have tension, and we have frictional forces. So the other type of force, which is our interest for today, are the force fields. For force fields, we don't need any contact. In as much as you are in the radius of the field, you experience the force. Examples of that are: if we have a magnet, this is the north and the south pole of the magnet. If we bring a metallic object very close to this magnet, we are going to notice that this magnet will attract this metallic object. That means that the object doesn't need to be in contact with the magnet before it experiences the magnetic force of the magnet. So that's what we are trying to say, that for force fields, we don't need a direct contact for the object to experience the force. Another example of force field is electric forces, which act the same way as the magnetic forces. And then the third one is the gravitational field, which is our main interest today. So what is a gravitational field? A gravitational field is a region or space where gravitational forces are felt. Every object is believed to be in its own gravitational field. What I mean by that, or what we mean by that, is just that every object in space will attract another object in space with a force that acts in opposite directions. In the same way, the Earth would also attract the Moon, and the Moon would also attract the Earth. It is believed that these forces are what keeps all objects in the universe in their position. And Newton helped us in calculating the force of attraction between these two objects. If this object is mass m1 and the other object has a mass of m2, Newton was able to deduce that the force of attraction between the two bodies is directly proportional to the product of their masses and inversely proportional to the square of their distance apart. Let's say this is the center of this mass, and this is the center of the other mass. Then their distance apart will be represented as r. So the Newton's law of universal gravitation states that the force of attraction between two masses is directly proportional to the product of their masses and inversely proportional to the square of their distance apart. So that means that if two light masses are in contact with themselves, the force is going to be low. That means that a high mass would result to a high force, and then a high radius would result to a low force. What we are just trying to say scientifically is just that as the mass increases, the force of attraction increases, and as their distance apart increases, the force of attraction reduces. If we introduce our constants here, we are going to have that F is equal to Gm1 m2 all divided by r squared, where G is referred to as the universal gravitational constant. And it has a value of 6.67 times 10 to the power of minus 11 Newton meter squared per kg. So let's move on from here. So mathematically, we are able to deduce that F is equal to Gm1 m2 over r squared, where m1 and m2 are the masses of the two particles measured in kilogram. G is the universal gravitational constant, and then r is their distance apart measured in meters. So let's take a look at this question. Two 5 kg spherical balls are placed so that their center are 50.0 centimeters apart. So the mass m1 is 5.0 kg and the mass m2 is also 5.0 kg because they have the same masses, and then their distance apart r is 50.0 centimeters. And then we are told to take the gravitational constant G as 6.67 times 10 to the power of minus 11 Newton per meter squared per kg. So from here, Newton was able to tell us that the relationship between the masses, the force of attraction, and their distance apart is represented as F is equal to Gm1 m2 over r squared. So the force of attraction F will be equal to 6.67 times 10 to the power of minus 11, which is the value of G, times m1, which is 5 kg, times m2, which is also 5 kg, all divided by their distance apart, which is r, which is 50.0 centimeters. But we have a problem here. The problem is that centimeter is not the SI unit for what? For distance. So that means we need to convert our centimeters to meters, which is the SI unit for distance. And we know that 1 meter is equal to 100 centimeter. So to convert this to meters, we have to divide by what? By 100. So 50 centimeter will be equal to 50 divided by 100. So that we now have our F to be equal to 6.67 times 10 to the power of minus 11 times 5 divided by 0.5 times 0.5. And if we do this, we are going to have F to be equal to 6.67 times 10 to the power of minus 9 Newton. 6.67 times 10 to the power of minus 9 Newton. So if we have two masses, M1 5 kg and M2 5 kg, separated by 50 centimeters, their force of attraction will be equal to 6.67 times 10 to the power of minus 9 Newton. So let's move on to calculate the mass of the what? The mass of the Earth. Or before we do that, let's take a look at this example 2. Determine the force of attraction between the center of the Sun, which is represented as ms, which has a value of 1.99 times 10 to the power of 30 kg, and Earth, mass of the Earth, is given as 5.98 times 10 to the power of 24 kg. Their distance apart is equal to 1.5 times 10 to the power of 8 kilometers. So we are told to calculate the force of attraction, F. Newton told us that the force of attraction, F, is equal to Gm1. F is equal to Gm1 M2 all divided by r squared. So if we impute the values of our parameters here, we are going to find out that F is equal to G, which has a value, it's a constant, it has a value of 6.67 times 10 to the power of minus 11 Newton meter squared per kg squared times M1. The value of M1, let's take M1 as the mass of the Sun, and let's take M2 as the mass of the Earth. So our M1 is 1.99 times 10 to the power of 30 times the mass of the Earth is 5.98 times 10 to the power of 24 kg, all divided by their distance apart is 1.5 times 10 to the power of 8, but we have to convert that to meters because I told you in the other example that the SI unit for distance is what is meters. So if we make use of our kilometers here, we are going to get the wrong answer. So we have to convert that to what? To meters. And how do we convert kilometers to meters? We know that 1,000 meters is equal to 1 kilometer. So therefore, 1.5 times 10 to the power of 8 kilometers will be equal to 1.5 times 10 to the power of 8 times 1,000. Since 1,000 meters is equal to 1 kilometer, then 1.5 times 10 to the power of 8 kilometers will be equal to 1.5 times 10 to the power of 8 times 1,000 meters. So this value is what we are going to use here now as our distance. So we have 1.5 times 10 to the power of 8 times 10 to the power of 3. Don't forget the square, because in our equation, what we have is r squared. So if we push further, we are going to get our F to be equal to 3.53 times 10 to the power of 22 Newton. If we do that, we are going to get 3.53 times 10 to the power of 22 Newton. So let's move forward. So as I said now, we want to state the relationship between our universal gravitational constants and our acceleration due to gravity. And in this subtopic, we are going to learn to calculate our small g, which is the acceleration due to gravity of the Earth. We are also going to learn to calculate the mass of the Earth, and then we are also going to learn to calculate the distance of every object from the center of the Earth. So, from the Newton's law of universal gravitation, which was given as F is equal to G m1 m2 over r squared. F is equal to G m1 m2 over r squared. We also know that every object in space falling down would move with an acceleration equal to the acceleration due to gravity, meaning that F, which is equal to ma, and since the object is falling down, the value of a will be equal to the acceleration due to gravity, because every object falling to the surface of the Earth must fall with an acceleration equal to the acceleration due to gravity. And from here we can deduce that F is equal to what? mg. Let's represent this as equation 1 and this as equation 2. So what we are going to do now is from equation 1, we know that F is equal to Gm1 m2 all divided by r squared, and from equation 2 we know that F is equal to what? mg. So since the values of F are both equal to this and this, what we want to do now is to equate those two values together so that we have Gm1 m2 all over r squared must be equal to mg. So one assumption we are going to make here is just that our m2 is equal to m. So that we now have Gm small m all divided by r squared must be equal to what? To mg. And from here we have m at both ends of the what? Of the equation, and m can cancel m here, so that we have Gm over r squared is equal to g. And this equation shows the relationship between the big G, which is the universal gravitational constant, and our small g, which is the acceleration due to gravity. And then from experiments, m is the mass of the Earth, and we can deduce that g is equal to g me over re squared, where me is equal to the mass of the Earth, and re is equal to the radius of the Earth, which shows the distance of every object in space from the Earth. So let's move further to this example 3. So we want to determine the mass of the Earth. If the radius of the Earth is approximately 6.38 times 10 to the power of 6 meters, g is taken as 6.67 times 10 to the power of minus 11 Newton meter squared per kg squared, and then small g is taken as 9.8 ms squared. The truth is that from this equation, g is equal to gme over r squared. Knowing the values of g and this big G, the values which are g is equal to 9.8 ms minus 2, which is a constant. G is the acceleration due to gravity of the Earth, and every object falling to the surface of the Earth must move with this value. And big G, which was defined as the universal gravitational constant, is equal to 6.67 times 10 to the power of minus 11. Knowing these values, we can calculate the mass of the Earth and the radius of the Earth. So for this question, the question wants us to calculate the mass of the Earth. So if we cross multiply here, we are going to have gr squared is equal to gme, dividing both sides by g, because our interest is in mass of the Earth. Dividing both sides by g, then we have the mass of the Earth to be equal to gr squared over g. and that is equal to G is 9.8 times R is, we were told to take R as 6.6, we were told to take R as 6.38 times 10 to the power of 6 meters. So from here we have 6.38 times 10 to the power of 6 all squared, all divided by the value of G, which is 6.67 times 10 to the power of minus 11. And from there, the mass of the Earth will be 6 times 10 to the power of 24 kg, which is the approximate value for the mass of the Earth. And then every object on the surface of the Earth has a distance of 6.38 times 10 to the power of 6 meters from the Earth. Escape velocity. So escape velocity is defined. Escape velocity is defined as the minimum velocity required for an object to just escape the gravitational influence of the Earth. As we all know that every object that goes up must come down. Yes, but there's a certain velocity at which objects can be launched, and then they are going to escape the influence of the gravitational force of the Earth. And that is the principle, rocket, satellite, that is the principle that are all applied to them. So they are launched at a value of velocity which is equal to the escape velocity. If they are launched at this value, we are going to see that they are going to escape the influence of the gravitational force of the Earth. So our main focus today is to calculate that velocity. So, but first, we must learn to derive the relationship between the velocity and the and the other parameters we've mentioned earlier. So we can do that from we stated earlier that F is equals to Gm m over r squared. But before we move further, I would like to write all the equations we've proved at this point here. The first one we said was that F, I'll just write it at this little corner, F is equals to Gm m over r squared. We also proved that G is equal to Gm over r squared, where this is the mass of the Earth and this is the radius of the Earth. So let's go back to this proof. So we have that F is equals to Gm times m over r squared. And from here, our kinetic energy is equal to what? Force times distance, r. Recall that energy is a product of what? Of force times what? Distance. So the distance in this question is what? Is the value of what? Of r. And from here, kinetic energy is equal to what? Half mv squared, which is equal to our force. From here, our force is given as what? Gm m over r squared times small r. All I just did there is to equate my kinetic energy to be equal to force times distance. The force has a value of G mm over what? Over r squared times r. And from here, we're going to see that this r is going to what? Cancel one of the r's here, so that we have half mv squared is equal to G m. And then this m here goes with this m here, and then we have v squared is equal to what? 2gm. But GMR is equal to GR. GMR is equal to what? GR. How do I get that? From this part of this equation here, where we say that Gm over r squared is equal to G. from here, we can say that Gm over R times 1 over R, we've not changed anything here. Since it's R squared, R times R will still give us R squared, is equal to G. And from here, we can cross multiply and take this R to this side so that we have Gm over R is equal to Gr. So that is what we have here, that Gm over R is synonymous towards Gr. The R here was just represented as capital letter R, since we are dealing with the what? With the Earth, which is, and this R is represented as the radius of the Earth. So from here now, we can now say that our V squared, which is equal to 2GmR, is equal to 2Gr. And finally, we can say that V squared, which is equal to 2Gr, taking the square root of both sides, our V is equal to the square root of 2Gr. So using this equation now, we can calculate the escape velocity for Earth. But before we do that, I would like to use a different method to prove this equation here. We can also equate the potential energy to be equal to the kinetic energy. What we are just trying to do is what? Is to prove, using a different method, that V is equal to the square root of 2Gr. So our potential energy has a formula of mgh. Our h here is represented as what? As R, which is equal to still half mv squared. So that we have mgr is equal to half mv squared. M goes with m, and then we have gr is equal to half v squared. When we cross multiply, we have v squared to be equal to 2gr. And when we take the square root of both sides, we are going to have that what? V is equal to the square root of 2gr. So you can see that with a simpler proof, we were also able to calculate the escape velocity of the Earth. Although this is the method you are going to find in most textbooks, this method is also very correct. So let's move further to now calculate the numerical value of the escape velocity of the Earth. Don't forget that our formula is VE is equal to the square root of 2gr. So calculate the escape velocity of the satellite from the Earth's gravitational field. If G is equal to 9.8 ms minus 2, the Earth's radius, RE, is equal to 6.4 times 10 to the power of 6 meters. So we want to calculate the escape velocity of the Earth. Our formula is given as V is equal to 2gr, and from here, VE is equal to the square root of 2 times G has a numerical value of 9.8 times the radius of the Earth, that is the distance of every object from the surface of the Earth, has a value of 6.4 times 10 to the power of 6 meters. And if we calculate that, we are going to get a value of 11 kilometers per second, which is also represented as 11,000 meters per second. So that means that if I want to launch a satellite or a rocket into space, I must give it a velocity greater than the escape velocity, because the escape velocity is said to be the minimum velocity required to launch an object into space. So if the velocity of the satellite is less than this, then it's going to come back to the surface of the Earth. But if we give it a velocity greater than this, that means that it's going to escape the influence of the Earth's gravitational force. So let's take an example. Earth's gravitational force. So let's take a look at the effects of the Earth's gravitational field. So what are the effects of the Earth's gravitational field? So the first one we calculated is that we said that the Earth's gravitational field gives us a clue about the mass of the what? The mass of the Earth. So from the Earth's gravitational field, we can calculate the mass of the Earth, and that is as a value of 6 times 10 to the power of 24 kg. Without that formula, it would be very impossible to know that value. And then we can also calculate the radius of the Earth, which has a value of 1.5 times 10 to the power of 8 meters. And from there too, we were able to calculate the value of G, which has a value of 9.8 ms minus 2. So the Earth's gravitational field helps us to know these values. And aside that, it also keeps every object in what? In space, in their position. When we started this class, I told you that every object is in its own gravitational field. That means that every object would attract the other objects closest to him with the same force. And Newton was able to what? Was able to give us the value of the force using this formula. So in that sense, we can say that the Earth and the Sun and the Moon are all in their position due to the gravitational field of the universe. Without the gravitational field of the universe, then the Sun, the Moon and the Sun, the Moon and the Earth might not be able to what? To keep orbiting in their what? In their position. So the gravitational field of the universe helps them to be what? To be put in their what? In their place. And then another effect is that we were able to calculate the escape velocity of the what? Of the Earth. Without this value, then we won't be able to study some of these astronomical bodies like Pluto, like other astronomical bodies. We won't be able to what? To have a clear study about them, because we make use of these satellites and rockets. What we send them into space so that we can get data about what? About them. And before we can do this, we need to what? We need to launch them with a what? With a velocity greater than the what? Than the escape velocity. So you can see that the gravitational field has a lot of what? It has a lot of benefits to us. So let's move to these practice questions. So the first practice question is telling us to state the Newton's law of universal to the product of their masses and inversely proportional to the square of their distance apart. And we can write that mathematically as F is proportional to the product of their masses and is inversely proportional to the what? To the square of their distance apart, where M1 and M2 are the masses of the bodies, and R is their distance apart. And from there, if we bring in our equality sign, then our constant comes into place, and then we have that F is equals to what? G M1 M2 over R squared. So the Newton's law of universal gravitation states that the force of attraction between two masses is proportional to their products and inversely proportional to their square. And mathematically, it is written as this. And then from there, we can say that F is equals to G M1 M2 over R squared, where G is equal to the gravitational constant. So the B part of the question says that we should define the gravitational field of the Earth. The gravitational field of the Earth is just a space or region where the effects of gravitational forces are what? Are felt. Simply put, it is just a region where gravitational force is what? Is felt. So let's move to the next practice question. So derive the equation relating the universal gravitational constant g and the acceleration of free fall small g at the Earth's surface. Don't forget that we proved this equation, and then I said that all we need to do is what? Is to equate, since we know that F is equals to what? Gm over r squared is equal to what? Mg, where this is the force of attraction between two bodies on the Earth, and this is the what? This is the force on any object experiencing free fall. From here, m cancels m, and then we have that g is equal to what? Gme over r squared, where this is the relationship between what? Between the universal gravitational constant and the acceleration of free fall, g. Then the B part of the question is saying that we should state two assumptions for which the relationship A holds. The assumptions are: 1, the Earth is assumed to be spherical. Without the Earth being spherical, then this equation might not hold. Another assumption is that the Earth is assumed to be what? To be uniformly dense. Another assumption is that the mass of the Earth is assumed to be concentrated at the what? At the center of the Earth. The mass of the Earth is assumed to be concentrated at the what? At the center of the Earth. So moving to the next practice question. Define escape velocity. We define escape velocity as the minimum velocity required to launch an object into space. So escape velocity is the minimum velocity required to launch an object into space. So the B part of the question wants us to derive the equation for escape velocity and obtain its numerical value for the Earth. So I'm going to go with a simple, I taught us two methods to doing this. So the second one, I said let PE be equal to what? To KE. And we know that our potential energy, which has a formula of mass times acceleration due to gravity times distance r, is equal to kinetic energy, which has a formula of half times m times v squared. Since we have m at both ends of the equation, we can cancel them out, so that we now have gr to be equal to what? Half times v squared. So when we cross multiply, we have 2gr is equal to what? V squared. And since we are calculating the escape velocity of the Earth, then this r can be represented as the radius of the Earth, and v as the what? As the escape velocity of the Earth. Taking the square root of both sides now, we finally have that VE is equal to the square root of 2gr. The question also said we should calculate the numerical value. Calculating the numerical value, we are going to get the escape velocity of the Earth as 11,000 meters per second, meaning that any object that is to be launched into space must have a velocity greater than 11,000 meters per second. So question C says we should state two differences between the universal gravitational constant and free fall. We want to state two differences between the universal gravitational constant and free fall. The first difference is just that they have different units. Let's start from there. They have a different unit, and from our discussion today, we should know that G has a unit of m squared kg minus 2, and then G has a unit of what? Of ms minus 2. And G is also referred to as the what? As the force per unit mass of the what? Of the body. So they have different units. Then another difference is that Another difference is just that G is a universal constant. G is a universal constant. Is a universal constant, while G is the acceleration due to gravity of the Earth. Acceleration due to gravity of the Earth. So those are the two differences between the big G, which is universal gravitational constant, and the small g, which is the acceleration due to gravity. So G has a unit of nm squared, kg minus 2, and small g has a unit of ms minus 2. And then the other one is that big G is a universal constant. That means it applies to the universe, while small g is related to the what? To the Earth. That means when we get to other parts of the what? Of the universe, then we are going to have a different value for what? For G. So a rundown of everything we've talked about today before we go for break. We say that every object in space attracts themselves with a value, with a force of attraction that has a value of F is equals to G m1 m2 over r squared. That means that you can calculate the force of attraction between you and the person near you by what? By knowing the masses of what? Of your mass, the mass of the person near you, and knowing the distance apart, knowing your distance apart. So the F is equal to what? G, which has a value of, it's a constant, 6.67 times 10 to the power of minus 11. So use that to multiply the mass, your mass, with the mass of the person next to you, and divide by the what? By the square of your distance apart from the person. And you are going to calculate the force of attraction between you and then the person. And from there, we also derive the formula relating G, which says that G is equal to Gm over what? Over r squared. And G is also referred as to the force per unit mass acting on a body. And from there, we talked about escape velocity, which is the minimum velocity required to launch an object into space. And then we close it by what? By learning some effects of the gravitational fields. And we were made to know that the moon, the Earth, and the sun all stay in their position due to what? Due to the gravitational field of the what? Of the universe. So thank you for. We are going to go on a short break now. When we come back, we are going to take your questions. Thank you very much. Okay, so Emilio, we got your question. The escape velocity is not energy. It's the minimum velocity required to launch an object into space. And Monira, thank you for answering that question for us. That's correct. Just that the force of attraction is directly proportional to the product of the masses. Yes, you got that right. But it is also inversely proportional to the square of their distance apart. So let me take that again. The escape velocity is the minimum velocity required to launch an object into space. And then the force of attraction is what is directly proportional to the product of their masses and inversely proportional to the square of their distance apart. So to round up, let's take this assessment question now. So calculate the force per unit mass on the Earth's surface. ME, the mass of the Earth, has a value of 5.98 times 10 to the power of 24 kg. 5.98 times 10 to the power of 24 kg. And then the radius of the Earth has a value of 6.38 times 10 to the power of 6 meters. And G is given as 6.67 times 10 to the power of minus 11 Newton per meter squared per kg squared. So the force per unit mass is also given as what? As g. Our small g, which is the acceleration due to gravity, is also known as the force per unit mass. And this is equal to what? To gm over r squared. So if we put in these values, then we are going to have that our g is 6.67 times 10 to the power of minus 11 multiplies the mass of the Earth, which is 5.98 times 10 to the power of 24 kg, all divided by r, which has a value of 6.38 times 10 to the power of 6 meters, all squared. And if we do this, we are going to get a value for g, which is 9.8 ms minus 2, which is the acceleration due to gravity of the Earth, and is synonymous to the what? To the force per unit mass acting on the Earth's surface. So thank you for attending today's section. For further reading and reference, please select Gravitational Field, Lesson, Content, available on learnathome.ng. So thank you for your time. Please join us next week. Thank you.